Covalent bonding and Lewis structure. So in the previous video, we talked about the 3 types of bonding briefly and then went into a lot of detail about ionic bonding. Now we talk about covalent bonding and drawing Lewis structures to show how each of these elements can come together to fulfill their octets. There's 3 types of bonds that you'll see. Single bonds, which is when you have the carbon that has the 1 electron and the hydrogen that has the other. They form a bond. Single bond, each bond has 2 electrons. Double bond is when you have the 2 electrons here that come together to form 2 bonds, and then triple, you have 3. Now, each bond has 2 electrons, so that's called bonding electrons. When you have 2 electrons like this next to each other, those are non-bonding electrons. Also, lone pairs. Now, a lone pair is always and only when you have 2 electrons together. Non-bonding electrons could be if you just had a singular one. That's kind of how we help characterize a Lewis structure. So then, let's actually, before we go here, let's walk through going and drawing a Lewis structure. So starting off kind of small, take a moment to draw the Lewis structure for, let me get my little marker, hydrochloric acid. So I have hydrogen and I have chlorine. I know hydrogen has 1 valence electron. Chlorine has 7. 1, 2, 3, 4, 5, 6, 7. In order for them to form a bond, hydrogen and chlorine will make a bond, and this is my Lewis structure. Now, what about hydrofluoric acid and diatomic fluorine? Let's draw the Lewis structures for those. So I have my hydrogen here, my fluorine. They're going to bond once, and then I have my fluorine and fluorine. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. They bond once. Now, these are also covalent bonds, but what's the difference? What do you notice? Fluorine is way more towards the right on the periodic table than hydrogen. I know that fluorine has a larger ionization energy than hydrogen, meaning that it does not want to give up its electron, where hydrogen does. These are the exact same, though there's no difference in a trend. Now, fluorine, there's a new term, is more electronegative than hydrogen. So it pulls more of the electron towards itself, making this unequal sharing. So it's a covalent bond, but it's not a covalent bond where the electrons are completely shared. Fluorine and fluorine here are completely equal, so this is just a covalent bond. Since there's absolutely 0 difference between these 2 fluorines, we call this a pure covalent bond. Now, the way that we show that difference in electronegativity and bond polarity is through showing a partial charge. Here, since we know that hydrogen gives up its electron a lot more easily than fluorine, it gets a partial positive charge. Since there's 2 electrons here, right, if I draw my little 2 dots, that make up this bond. But this electron is pulled a little bit more towards the fluorine. So then fluorine technically feels the force of 2 negative charges, making it more negative. So we give it a partial negative charge, and hydrogen gets a partial positive charge. Because of this unequal sharing, this is a polar bond. This all stems from also electronegativity. Electronegativity is an atom's ability to attract electrons to itself in a chemical bond. That results in a polar bond if it's still covalent or ionic. So when the electronegativity is so large that the element is so much more negative than the other element, it's just going to take the electron and be ionic. If it's just in that range of still sharing, it's polar. The electronegativity increases across the period on the periodic table, and it decreases down. So I always like to draw, so if this is my little periodic table, it goes like this. It increases up and right. Fluorine is my most electronegative element, and francium is my least. So fluorine wants most electrons. Francium wants to get rid of its electrons. Here's a little electronegativity chart, and a few things that I want you to know. through these numbers, you can calculate your change in electronegativity. When your change in electronegativity is less than 0.4, you have a non-polar bond. When your electronegativity difference is equal to 0.5 to 1.7, you have a polar bond. When the electronegativity difference is greater than 1.7, you then have an ionic bond. And when the electronegativity difference is equal to 0 for two of the same elements, you have a pure covalent bond. So we would look at two of these elements coming together based off of these differences, whether they're pure, ionic, polar, or nonpolar. Because it tells us, does the electron get completely transferred? Is it kind of being unequally shared? Is the difference not large enough for them to be not shared unequally? Or is it just purely, completely equal? Dipole moment. Now, in my little picture before of my hydrogen and fluorine, I had this. We already know that hydrogen is partially positive and fluorine is partial negative. Another way that we can show polarity is through something called a dipole moment. The way that we show that is we point an arrow to the more electronegative element with a little dash through the ending of the positive side to show you this is the more positive, and all the electrons are pushing towards the more electronegative element. The degree of polarity is something that can actually be calculated. It represents how much polarity you have. So in a bond, it depends on the electronegative difference between the two bonding atoms. We can quantify this through a dipole moment, which gives the distance, the r, between the two atoms and the charge that you have. Another way that we can characterize is through percent ionic character. By comparing the actual dipole moment to what the dipole moment would be if you had a complete transfer. So if we look at this equation again, we can calculate this for what we have, right? Based off if we have the actual radius. Then if we calculate this again for, let's pretend like this electron from my hydrogen is completely transferred to my fluorine, what would the dipole moment be then? You compare those to then get a percent ionic character. What it actually is to what it would be if the electron was completely transferred. Percent ionic character is the ratio of the bond's actual dipole moment to the dipole moment it would have if the electron were completely transferred from one atom to the other. Putting kind of most of this together, let's look at these structures. Cl2, that's chlorine and chlorine. Electronegativity difference is 0. We know this is pure covalent. The dipole moment is 0 because there would be no dipole because there's no change in electronegativity. ClF, electronegativity difference is 1. You have a dipole moment of 0.88. Hydrogen fluoride, electronegativity difference is 1.9. So 1.0, that's in that range of 0.5 to 1.7. So this is polar. And therefore, you see an increasing of dipole moment. HF is also, it's actually greater than the 1.7, so it can be actually considered to be ionic. However, since hydrogen is a nonmetal, we still say this is polar. And then lithium fluoride is ionic because it's greater than 1.7. Something I want to point out to you is those numbers, 0.5, 1.7, they sometimes vary. Other texts say that greater than 2 is ionic, and anything less than that would be polar. That's why 1.9 is still okay to say polar. But what I want you to look at is the dipoles. So for pure covalent, 0. Then you have polar, but it's not necessarily a large difference. Then you get to almost being ionic, jumps up pretty high, and then you have ionic where there's a huge jump in the dipole because that would mean that the electron was completely transferred. Let's go back to Lewis structures. So we kind of started characterizing Lewis structures, thinking of how the electrons will be shared. Now let's go through the process of drawing the Lewis structure for ammonia, NH3. All right, so first step is you can write the skeletal structure I like to do is calculate my total number of valence electrons. So I know nitrogen's 5 and hydrogen's 1, but I have 3 of them. And this gives me 8 valence electrons total. Now, if I go to the side here, I know nitrogen has 5 valence electrons because it's in group 5. So 1, 2, 3, 4, 5. This means that nitrogen can make 3 bonds. Hydrogen has the 1 valence electron. It can only make 1 bond. So I have to pick my central atom. The less electronegative element, or the one that can make the most bonds, is going to go into the middle. So nitrogen's going to go into the middle, and I have my 3 hydrogens around it. Now my skeletal structure will be just to bond them together. Now my next step is satisfy my central atom for the octet. 2, 4, 6. Since each bond has 2, I count for nitrogen 2, 4, 6. Well, nitrogen needs 8 to be satisfied, so I have to have a lone pair here on the top. Hydrogen needs 2 to be satisfied. Each hydrogen is bonding, so each hydrogen is happy, and now my nitrogen is happy with that lone pair, and I only have used my 8 valence electrons. Now, there's numerous numbers of ways that you can draw Lewis structures. You can draw yourself a skeletal structure once you determine your central atom, and then satisfy your central with an octet, and then go to your outer elements. Another way that you could do this is, I know nitrogen's my center. I know nitrogen has 1, 2, 3, 4, 5 valence electrons. I know that I have my 3 hydrogens around, and each hydrogen only has 1. Well, then it just becomes connecting the dots. This electron is going to bond with this electron, this will bond here, and this will bond here. Now, when you see that some of the elements don't have complete octets, that's when you'll then make more bonds, double or triple, to give each element a satisfied